Welcome back to the Deep Dive. If you're working through your Aviation Maintenance Technician General course right now, you know it's all about building that essential toolkit, doesn't it? The skills you'll rely on throughout your career.
That's right.
Today we're diving into two critical languages every AMT needs to speak fluently: applied math and aircraft blueprint interpretation.
Yeah, absolutely. And look, for a lot of students, math, technical drawings, they can seem like, hurdles.
Right. A bit intimidating sometimes.
For sure. But honestly, they're your most direct path to doing the job safely and correctly. So our mission today really is to unpack this stuff, cut through the textbook jargon.
And show you, the AMT student, why this matters, how it's used day to day.
Exactly. Make it actionable.
So the moment you actually step into the hangar, the need for math becomes pretty obvious, right? This isn't just theory. It's about precision.
Oh, absolutely. And what kind of precision are we talking about?
Yeah, tell us about that.
We're talking about measurements that are, well, non-negotiable. For airworthiness, think about a turbine engine.
Okay.
You might be measuring clearances, tolerances, sometimes down to a 10,000th of an inch.
Wow. That's tiny.
It is. And if you can't handle those decimal values correctly, you just can't do that inspection, period.
Right.
But it's not just high precision stuff. It's everyday things too. Calculating fuel volumes, figuring out surface area for a sheet metal patch, working with fractions.
So it's fundamental.
Totally fundamental. These are the tools you use constantly.
Okay, so let's unpack this. Let's make this stuff immediate and useful.
Yeah.
Think of this as your shortcut from the classroom to the shop floor reality. All right, part one. The essential math toolkit. We're talking precision measurement.
Let's start right at the beginning. Whole numbers, basic operations. Add, subtract, multiply, divide.
Seems simple, but even here, that concept of place value is crucial, isn't it?
It's the bedrock. Absolutely. Yeah. Imagine you're reading a micrometer. It says 0.5123 inches. If you don't instantly get that the 3 is 10,000ths, you might round wrong or misunderstand how critical that tiny digit is for a tight tolerance.
So place value helps ensure you're adding apples to apples when you line up numbers for addition or subtraction.
Exactly. You have to align those decimal points or those columns correctly.
And division. Sometimes you get remainders, like distributing parts.
Yeah, and that remainder isn't just leftover junk. Take that example. 218 landing gear bolts. 7 aircraft.
Okay.
You divide it out. Each plane gets 31 bolts. Simple enough.
But there's one left over.
Right. That single bolt. It's not nothing. It tells you something. Maybe an inventory issue. Maybe the kits weren't packed right. Interpreting that remainder is part of the job.
Good point. Okay, let's shift gears to fractions. Super common in aircraft structures, right? Sheet metal especially.
Oh, everywhere.
Right.
Fractions. N over D, numerator over denominator. And the golden rule,
the denominator, D, can't be 0.
Cannot be 0. And when you're adding or subtracting them, you absolutely must find the least common denominator, the LCD.
This isn't just busy work from school.
No way. Finding the LCD is what makes your calculation accurate. It ensures you're adding parts, and it often simplifies the answer into something you can actually measure easily on the floor.
Okay, practical example time. Adding fractions. Let's say you're figuring out the total thickness of a panel. You've got 332-inch aluminum plus a 164-inch paint coat.
Right. You need that final dimension, maybe for picking the right rivet length.
So the denominators are 32 and 64.
Largest one is 64, so that's our likely LCD. We need to convert 332 into 64ths. Multiply top and bottom by 2.
Gives you 664.
Exactly. Now you can add the paint, 664 plus 164.
That's 764 inches total thickness. Makes sense. You can't just add the 32 and 64.
Definitely not. You got to speak the language of common parts.
All right, subtraction. This often comes up with tolerances, which links directly to safety. Let's take rigging an aileron. Manual says the droop tolerance is 78-inch plus or minus 15-inch. What's the absolute minimum droop allowed?
Okay, so we need to find the lower limit. That means we subtract the allowance. 78 minus 15.
Denominators 8 and 5, the LCD is 40.
Right, so 78 becomes, multiply by 5, 3540, and 15 becomes, multiply by 8, 840.
Okay.
Now, subtract. 3 offshore 540 minus 840 gives you 2,740 inches.
So 2740 is the minimum acceptable droop.
That's the line. If you set it any lower, say 2640, you're outside the engineered safety limits. It's compliance work, really, just using basic math.
Okay, moving on. High-precision parts often mean decimals. Base 10 system, powers of 10. Seems more intuitive sometimes.
It can be, especially for addition and subtraction, like in electronics. The rule is simple. Line up the decimal points vertically.
Right, like summing resistors in series, say 2.34 ohms, 37.5 ohms, and 0.09 ohms.
If you don't align those decimals properly, your total resistance will be way off. Done correctly, you add them up.
And you get 39.93 ohms for RT, total resistance.
Exactly. Simple alignment, crucial result.
Multiplication, though. Different story. Alignment doesn't matter there, like calculating power. Watts equals amps times volts.
Yep.
PIE, say 9.45 amps times 120 volts.
Here are the rules about counting decimal places. 9.45 has 2 decimal places, 120 has none.
So the answer needs 2 decimal places.
Correct. You multiply 9.45 by 120, you get 1134. The answer must be 1134.0000000 watts. That counting rule stops you from being off by factors of 10 or 100.
Which brings us to rounding. You calculate a value, but you often need to round it to match your measuring tool or the required spec.
And rounding correctly is critical. The rule, look at the digit just to the right of your target place value. If it's 5 or more, round up. Less than 5, leave it.
Okay, example. Calculate a shaft diameter as 2.1938 inches. Spec says report to the nearest tenth.
Okay, the tens place is the 1. The digit next to it is 9, since 9 is 5 or greater.
You round the 1 up to 2, so 2.2 inches.
Perfect. Now another one, 3.1648 centimeters, round to the nearest hundredth.
Hundredths place is the 6. Digit next door is 4.
And 4 is less than 5, so the 6 stays as it is.
Result, 3.16 centimeters.
Exactly. These rules prevent confusion between a super precise calculated value and what you can actually measure or need to report.
Okay, one really common task for mechanics, converting between these formats, especially decimal blueprint dimensions back to fractions for your tools.
Yeah, you have to do this all the time. Your standard steel rule, probably marked in 64ths of an inch.
Right.
So even if you have digital calipers, you need to understand how decimals relate to those fractional marks, especially on older drawings.
So how do we reliably convert a decimal, like something from a Trent, into the nearest 64th?
The quickest way is to think of it as finding a fraction out of 64. You take the decimal value, multiply it by 64.
Okay.
The result you get, round it to the nearest whole number. That whole number becomes your new numerator, over 64. Then simplify the fraction if you can.
Let's try that with a real task.
Yeah.
Selecting an undersized drill bit. Common practice is to drill 1/64 under before reaming to final size, right?
Correct.
For accuracy. So the blueprint calls for a final reamed hole of 0.763 inches. What drill bit do we need to start with?
Okay, first step. Translate that target decimal, 0.763, into 64ths. Multiply 0.763 by 64.
Let's see, 0.763 times 64 is 48.832.
Right. Now round that 48.832 to the nearest whole number. That's 49.
So the final size is roughly 4,964ths of an inch.
Approximately, yes. Now, we need to drill undersized by 164th.
So we subtract 164 from 4,964.
Which gives us 4 down and 864.
And 4 tan and 864 simplifies, doesn't it? Both divisible by 16.
Exactly. Divide top and bottom by 16, you get 34.
So you need a 34-inch drill bit.
That's the one you grab. See how we used both decimal precision from the print and fractional knowledge for the tool? That's a perfect example of the interface.
Okay, moving in slightly more advanced concepts. Ratios, proportions, percentages. Part 2.
Right. Ratios are just comparisons of two quantities. You can write them different ways, like a fraction, 57.
Or with a colon, 5.7.
Or just using the word 2, 5 to 7. And aviation specs are full of ratios.
Give us some key examples.
Oh, plenty. Engine design relies heavily on the compression ratio, maybe 10.1. It affects power, efficiency.
Wing design uses aspect ratio that's span versus chord length. Affects drag.
Yep. Combustion itself is the air-fuel ratio, often around 14.3 to 1 by weight for optimal burning.
And my personal favorite, especially if things go wrong, the glide ratio. Say 10.56 to 1.
Crucial for engine-out situations. Means for every foot of altitude lost, you travel 10.56 feet forward. Tells the pilot how far they can reach.
Life-saving math right there.
Absolutely. And in mechanical systems, like gearboxes, ratios determine speed changes. A gear ratio compares teeth numbers, like 8 teeth to 28 teeth, which simplifies to 2.7.
But the speed is inverse, right?
Exactly.
Yeah.
If the gear ratio is 2.7, the speed ratio is 7.2. The smaller gear spins faster. That ratio dictates how power is transferred.
Okay, that leads nicely into proportions, which are basically just two equal ratios used to find an unknown.
And proportions are the absolute bread and butter for things like fuel planning. Classic example. A plane uses 24 gallons to fly 300 miles. How much fuel for a 750-mile trip under the same conditions?
Okay, set up the proportion. 300 miles is to 24 gallons, as 750 miles is to G gallons are unknown.
Right. Then you cross multiply and divide. Multiply the diagonal,
Yep.
750 times 24.
Which is 18,000.
Now divide that by the remaining number, 300.
18,000 divided by 300 is 60.
So you need 60 gallons. This isn't just academic. It's a fundamental check to make sure you have enough fuel for the flight. It's a regulatory thing, really.
Makes sense. All right, percentages. Percent means parts out of 100. Converting decimals to percentages move the decimal two places, right?
Yep, pretty straightforward. But the real application is in things like calculating efficiency or losses. How well is a component performing?
Okay, example. Checking engine health. Say you have a small 12-horsepower engine on the test stand, but is only putting out 10.75 HP. What's its efficiency?
We need to find what percentage 10.75 is of 12.
So divide the actual output by the rated output, 10.75 divided by 12.
Exactly. That gives you 0.8958.
Move the decimal two places,
Okay.
89.58%.
Right. Now, if the maintenance manual says anything under 90% efficiency means it needs an overhaul,
Then that calculation just dictated a major maintenance action.
precisely. The percentage isn't just a number, it's a diagnostic tool that tells you whether the component is healthy or not.
Okay, next up. Signed numbers. Positive and negative. Crucial for things like weight and balance calculations, right?
Absolutely essential for standardizing records. In weight and balance, any weight you remove from the aircraft is treated as a negative number.
Why is that so important?
Consistency. If the aircraft starts at 2,000 pounds and you take out a 3-pound radio rack and a 10-pound transceiver,
The calculation is 2,000 plus -3 plus -10.
right, which equals 1,987 pounds.
Yeah.
If you don't use those negative signs correctly, your paperwork won't match the actual aircraft weight. That's a big problem, potentially a violation.
Got it. And signed numbers apply to environmental data too, like temperature.
Yep. Say it's minus 7 degrees Celsius on the ground in Denver. Pretty cold.
Okay.
And the forecast says it'll be 20 degrees colder at cruising altitude. What temperature will the aircraft systems face?
That's -7 minus another 20.
Or think of it as adding a negative, minus 7 plus negative 20, which equals...
Minus 27 degrees Celsius.
Exactly.
Mm.
And knowing that is vital for things like anti-icing systems and how the aircraft will perform.
Okay. So when calculations get more involved, we move into algebra, using formulas with variables.
Yeah. Things like Ohm's law, lift formulas, structural stress, they all use algebra. The core rule, the one you absolutely cannot forget, is balance.
Whatever you do to one side of the equation, you must do to the other.
You got it. Keep it equal. But the real place people get tripped up, I find, is the order of operations. PEMDAS.
Parentheses, exponents, multiplication, division, addition, subtraction. Sounds easy.
But it's tricky, especially the MD and AS parts. You have to do multiplication and division together in one pass, working from left to right.
Not all multiplication first, then all division.
No. Same for addition and subtraction. One pass, left to right. Let's take 10 minus 4 times 3 divided by 2.
Okay. Left to right for MD. First is 4 times 3, which is 12.
Right. Now the equation is 10 minus 12 divided by 2. Next MD step.
12 divided by 2 is 6.
Good. So now it's just 10 minus 6.
Which is 4.
C. If you did the division 32 first, got 1.5, then multiplied by 4, you'd actually still get 6 in this case. Need a better example to show the error. Point is, stick to the left to right sweep for MD and AS.
Okay, let's look at a really critical aviation example where order and just following the formula matters. Calculating total capacitance, CT, in a series circuit, the formula is that reciprocal one. 1 CT equals 1 C1 plus 1 C2 plus 1 C3.
Ah, yes, the classic trap. So you plug in your capacitor values, say 0.1, 0.015, and 0.05 microfarads.
Okay.
You find the reciprocal of each one, then you add those reciprocals together. Let's say the sum comes out to 96.66.
So CT is 96.66 microfarads.
That's the mistake. So many people stop there. But look at the formula again. You just calculated 1 CT.
You haven't solved for CT itself yet.
Exactly. The final crucial step is to take the reciprocal of that sum. You need to calculate 1 divided by 96.66.
Which is about 0.01034 microfarads.
Right. A tiny number. If you reported 96.66, you'd be off by a factor of over 9,000. That's not just wrong, it's dangerously wrong if you're choosing components based on that calculation. You failed to complete the algebra.
Okay, let's move into geometry. Area, volume, trigonometry. Started with area essential for things like sheet metal repairs, right?
Yeah.
Calculating how much material you need.
Absolutely. Basic formulas. Rectangle is length times width. Square is side squared. Triangle is half base times height. You need these to figure out coverage.
And circles. Like finding the area of an engine cylinder bore. Formula is pi times radius squared.
Yep, per. So if the bore diameter is 5 inches,
Radius is half that, 2.5 inches.
right, so pi times 2.5 squared. That gives you a cross-sectional area of 19.635 square inches. You might need that for calculating pressure or forces inside the cylinder.
Good example. What about wing area? Formula is area span times mean chord. But there's a catch sometimes with units.
Always watch the units. If the span is, say, 50 feet, but the mean chord is given as 6 feet 8 inches.
You can't just multiply 50 by 6.8 or something. You have to convert the inches first.
Exactly. 8 inches is 812 of a foot, or about 0.67 feet. So the mean chord is really 6.67 feet.
Now you can multiply. 50 feet times 6.67 feet.
Gives you a wing area of 333.5 square feet. Skipping that unit conversion is an easy way to mess up performance calculations badly.
Okay, spanning to 3D. Volume, measured in cubic units. Big application for AMTs is engine displacement, right?
Definitely. Piston displacement is essentially the volume of a cylinder. Formula, times radius squared times height. But here, the height is the stroke length.
So bore becomes I times bore 2 times stroke.
Precisely. Let's use the example. 5.5-inch bore, 5.4-inch stroke.
Radius is half the bore, so 2.75 inches. Square that, times pi, then times the 5.4-inch stroke.
Do the math, and you get 128.29 cubic inches. That's the displacement for one cylinder.
So for an 8-cylinder engine.
Just multiply by 8. Gives you 126.32 cubic inches total displacement. And that number is key for classifying the engine, understanding its power potential.
Finally, trigonometry. Right triangles. SOH, CAH, TOA, sine, cosine, tangent. And the Pythagorean theorem. A plus B equals EC1. Where does this pop up?
Structural analysis, bracing, component fit, and Pythagoras is great for solving practical logistics problems, like can you fit a large flat object through a smaller doorway diagonally?
Ah, the classic problem. Example. You have an 8-foot square steel plate. The cargo door is 7 feet wide by 5.5 feet tall. Will it fit?
Okay, the plate is 8 feet across its diagonal too. Well, close enough for this. The door opening forms the legs of a right triangle. A is 7 feet, B is 5.5 feet. We need to find C, the hypotenuse, which is the diagonal opening of the door.
So A plus B bead light, that's 11 squared, 49 plus 5.5 squared, 30.25.
Add them up. 49 plus 30.25 is 79.25. That's chi squared,
Now take the square root of 79.25.
which is about 8.9 feet.
So the diagonal opening of the door is 8.9 feet. The plate is 8 feet wide.
It fits. Just barely maybe, but trigonometry confirms you can load it diagonally. That's a real-world check you might need to do.
Okay, let's switch gears completely. Part 3. Decoding the blueprint language. Aircraft drawings.
The second essential language. And the environment has changed massively, hasn't it? From drafting boards to digital models.
Totally. We need to know the acronyms. CAD, CAM, CAE.
Computer-aided design, drafting, manufacturing, engineering. It's all about using software like CATIA, SolidWorks.
What's the big advantage of these digital tools?
Interference checking. Designers can digitally assemble the entire aircraft or sections of it and see if parts clash before anything is manufactured. It saves enormous amounts of time and money by catching errors early.
So the drawing you look at on a tablet might be a fully rotatable 3D model.
Often, yes, giving you way more information than a static 2D paper drawing ever could. But regardless of the format, the types of drawings and their purpose remain fundamental.
Right. The 3 main pillars AMT students need to get.
First, the detail drawing. This is laser focused on one single part. It gives you everything needed to actually make that part. Dimensions, material, finish, tolerances.
Okay, one part, how to make it. What's next?
The assembly drawing. This shows how 2 or more detail parts fit together. Think of a piston, pin, and connecting rod. It shows their relationship, how they assemble.
But not necessarily where that whole assembly goes in the plane.
Not usually. That's the job of the third type, the installation drawing. This shows the final position of a completed assembly or component in the aircraft, referencing key locations like fuselage stations or water lines.
So different drawings for different tasks. Making a part, putting parts together, finding where the whole thing goes.
Exactly. A machinist needs the detail, a mechanic assembling needs the assembly, and someone troubleshooting or locating damage needs the installation drawing.
Sometimes just looking at the outside isn't enough, though. We need to see inside. That's where sectional views come in.
Right. Sectional views, imagine cutting the object open to reveal internal features. There are different types. A full section cuts clean through. A half section is clever, used only for symmetrical objects. It shows half the view as an external view, and the other half cut away as a section. Saves drafting time, but gives you both internal and external info.
Like for a pulley or something symmetrical.
Perfect example. We also have revolved sections, where a cross-section shape is turned 90 degrees and drawn right on the main view. Or removed sections, where that cross-section is pulled off to the side and often drawn larger for clarity. Useful for showing the exact shape of things like wing spars.
Every drawing needs an ID, right? That's the title block, usually bottom right corner.
Yep, it's the drawing's passport. Absolutely critical information lives there.
Like what specifically?
The drawing number essential for finding the right print. The name of the part. The scale, though, always trusts the written dimensions over measuring the drawing itself.
Good tip.
The date and revision level, vital to make sure you're using the current approved version, the firm or company name, and the approval signatures or names, draftsman, checker, engineer. It shows traceability.
Okay, back to where math meets drawings. Tolerances and allowances. The plus-minus numbers that define acceptable limits.
This is where precision is legally defined on the print. Tolerance itself is the total amount of variation allowed. It's the difference between the maximum and minimum acceptable size.
Let's use that example again. Nominal size, 0.225 inches, with allowance of plus 0.00025, match 0.00005.
Okay. The maximum limit is 0.225 plus 0.0005 equals 0.2275 inches.
Minimum limit is 0.225, 0.0005 equals 0.2245 inches.
Right. So the total tolerance, the whole window of acceptability, is the difference between those, or you just add the plus and minus allowances. 0.00025 plus 0.003001. No questions aren't precise enough for most tolerance work.
Lastly, for finding things on the aircraft itself, we use that coordinate system, station numbers.
Yeah, the aircraft's built-in GPS, essentially. 3 main references. First, fuselage station, FS.
Measured in inches from a starting point, the datum, often the nose or firewall.
Usually, yes, gives you the fore and aft position. Second is buttock line, BL.
That's left or right of the aircraft center line,
Yeah.
LBL or RBL.
Correct. Horizontal position off the center. And third is waterline, WL.
Vertical position, measured up from a reference plane, like the ground or cabin floor.
Typically, yeah. So if damage is reported at, say, FS 380, RBL 40, WL 105.
Any technician knows exactly where on the fuselage to look.
Exactly. It's a standardized language, crucial for maintenance records, AD compliance, everything.
All right, part 4. Visualizing and communicating technical info. How do drawings actually show the object?
Different methods, right?
Right. The most technically accurate is orthographic projection. This uses multiple 2D views, usually front, top, side, to show the exact size and shape without distortion.
But you have to mentally combine those views to picture the 3D object.
You do, and that's where mistakes can happen. A circle on the front view. Is it a hole going in or a boss coming out? You have to look at the other views, especially hidden lines, to know for sure.
So for easier visualization, we have pictorial drawings. Exactly. These try to show the object more like how the eye sees it. Perspective drawings look most realistic, but dimensions get distorted. Isometric drawings are very common in manuals.
Why isometric?
Because lines that are parallel on the object stay parallel in the drawing, and dimensions along the main axis are true scale. It gives a good 3D impression while still being dimensionally useful.
And for taking things apart and putting them back together.
Exploded views are priceless. You see these constantly in illustrated parts catalogs, IPCs, and maintenance manuals, PIMs.
They show all the parts separated but lined up in assembly order.
Precisely. Shows the relationship, the sequence, every little washer and O-ring. Absolutely essential for ordering the right parts and getting reassembly correct.
Okay, beyond showing objects, drawings also map out systems using diagrams. What's the difference between an installation diagram and a schematic?
Big difference, critical to understand. An installation diagram shows the physical location of components in the aircraft. Where is that pump actually mounted? But a schematic diagram shows how components are connected functionally within a system. It focuses on the principle of operation, the flow of electricity or fluid, regardless of physical location.
So for troubleshooting why the gear won't retract, you'd want the schematic first.
Usually, yes. It shows the sequence. Switch, relay, hydraulic valve, actuator. The schematic maps the logic of the system.
Got it. other diagrams?
Block diagrams simplify very complex systems using just rectangles for major components and lines showing inputs/outputs. Good for a high-level overview.
And wiring diagrams.
Super detailed maps for electrical circuits show every wire, connection point, often with wire numbers and color codes for identification, essential for tracing electrical faults.
And finally, flowcharts, especially for troubleshooting.
Yeah, two main types. Troubleshooting flowcharts use diamond shapes for yes-no decisions to guide you step by step to find a fault. Logic flowcharts use standardized symbols for analyzing processes, often seen in digital systems or software logic.
Okay, the drawings themselves rely on a visual language. Lines and symbols. You said it's like learning an alphabet.
It really is. Different lines mean different things based on their weight, thickness, and pattern. You have to recognize them instantly.
Give us some key line types.
Okay, center lines. Thin lines, alternating long and short dashes, mark the center of symmetrical parts or holes. Hidden lines. Medium weight dashed lines. Show edges or contours you can't see from that view. Crucial for understanding internal features.
If you miss a hidden line, you might miss a mounting hole inside.
Easily done.
Yeah.
Then you have cutting plane lines, thick lines, often with arrows, showing where a sectional view is cut from. They'll be labeled like section AA.
What about showing that part of an object is omitted? Maybe because it's very long.
Those are break lines. Short, irregular breaks use wavy freehand lines. Long, straight breaks use ruled zigzag lines. They just indicate continuity is broken to save space.
And the lines used for measurements.
Dimension lines, thin, solid, with the number in a gap, and extension lines, thin, solid, extending from the object feature to the dimension line. There are rules here too, like placing the longest dimension furthest out, dimensioning between centers for holes to keep things clear and readable.
Beyond lines, we use symbols as shorthand.
Big time saver. Material symbols use different cross-hatching patterns and sectional views to instantly tell you if it's steel, aluminum, cast iron, rubber, etc.
Shape symbols can show the cross-section profile of something like a structural beam, I-beam, channel, angle.
And electrical symbols are everywhere in schematics and wiring diagrams. A standardized symbol represents a relay, a switch, a motor, a circuit breaker, much more clearly than drawing the actual component would.
And bringing it right up to today. Technicians use digital images constantly, right? Like taking a photo of damage.
Absolutely. But there's a key technique emphasized. If you photograph damage, like a crack or corrosion,
You need to include something for scale in the picture.
always place a ruler, a coin, even standard hardware next to the damage before taking the photo. That provides immediate dimensional context for the engineer or supervisor looking at the image, who might be miles away. It makes the photo useful information, not just a picture.
Okay, we have covered a huge amount today, from basic arithmetic all the way to interpreting complex schematics. The big takeaway seems to be how tightly integrated math and drawings are.
They really are two sides of the same coin. The calculations give you the precise limits, the numbers you have to hit. The drawings give you the map, the location, the assembly order. You need both to do the job safely and correctly.
They really form the core of safety assurance and maintenance, don't they?
Absolutely. Mastering these fundamentals isn't just about passing your general course exams. It's about building the foundation for a safe and reliable career. Every calculation you double-check, every drawing symbol you correctly interpret, directly contributes to airworthiness.
So as you continue with your studies and get ready for hands-on work, here's something to think about.
Consider this. Aviation maintenance relies heavily on these two completely different systems for conveying critical information. Pure numbers for things like tolerances, that 0.003 of an inch window, and pure graphics for things like installation procedures or system logic. How does having both these precise languages, numerical and visual, reinforce that core aviation principle of redundancy?
That's interesting, like having two independent ways to verify the required outcome.
Exactly. You get the information numerically and you get it visually. What does that reliance on dual verification mean for safety? And maybe more provocatively, what happens if, someday, the number on the print seems to conflict with the picture? Which system do you trust? Something to keep in the back of your mind as you tackle your next maintenance challenge.